The Law 1.5 of Thermodynamics. Energy can be applied in an organized manner, such as construction work, resulting in a decrease in the system's entropy. It can be applied in a random manner, such as a bomb, resulting in an increase in the system's entropy. A statistical analysis of the problem provides this needed general principle. Statistically, entropy is logarithmically related to the randomness of a system, as shown in Formula 1. In this formula, S is entropy, K is Boltzmann's constant, which is 1.38 times 10 to the negative 23 power, joules per Kelvin, and omega is the number of equivalent microstates, that is, possible arrangements of the system. This formula for entropy is known as Boltzmann's formula. Here we have the formula for the change in entropy. Because of its logarithmic relationship to the number of microstates, omega 1 and omega 2 are divided by each other. Because of these relationships, the problem of applied energy is best dealt with statistically. Furthermore, any system consists of smaller parts with their own independent equivalent microstates, resulting in Formula 4, which is a multiplication of those microstates, where omega s is the total number of equivalent microstates, and the product of the number of omega n microstates of each of the distinct smaller parts. Plugging Formula 4 into Formula 1, that is, S equals K ln omega sub s, such that you get Formula 5. This forms the basis of analyzing what happens to the entropy of a system when energy is applied to it. The simplest possible system to analyze is one consisting of a single particle that is moved to a targeted location by the application of energy. The entropy of the applied energy is related to the accuracy with which it can place the particle, such that omega sub equals the number of locations, equivalent states, where the applied energy could actually place the particle. The result would be that the entropy of the single particle system after the energy is applied would be equal to the entropy of the applied energy, such that S sub S equals S sub E. Here is an illustration of this principle in action. It illustrates a single particle that has energy applied to it, aimed at the blue dot in the center. The variation here is a result of inaccuracy in the energy being able to apply the particle. Now, if we move up the number of possible states, the particle's relationship to the target state becomes more random. If we up it even more, it becomes more random still. Now, if we reduce the number of possible states, it becomes less random. Reduce it even more, and it becomes less random and remains closer to the central target. Reduce it even more, and while not quite centralized, it does still remain very close to it. Reduce it completely, and it remains entirely in the center. In a complex system, the entropy of the applied energy would be the sum of the entropy of the energy applied to each of the component parts of the system in accordance with Formula 5, such that if the energy were applied to each component part of the system perfectly, then the entropy of the system, after the energy is applied, would be equal to the entropy of the applied energy, resulting in SS equals, say. In the real world, this would not be the case since some energy is lost. Here is an example of a system that is more complex. In this case, the energy keeps rearranging the particles, but not in an accurate manner. Now, we increase the randomness of the energy, and the particles get even more randomized. Increase it even more, and it gets even more random. Reduce it, and it gets less random. Reduce it further, and it gets even closer to being spot on to the target dots. Reduce it to 0, and like before, it gets right on the dots. This illustrates this principle in action. However, at some level, this process could be modeled such that some individual components of the system get energy applied to them, while others do not. In such a model, each component would have one of two possible outcomes. 1. The component gets energy applied such that omega 2n equals omega, and the component does not get energy applied such that omega 2n equals omega 1n. So, when S sub S2 is calculated by Formula 5, that the total energy of a system moves towards the entropy of the applied energy, such that delta S sub max equals S sub E minus S sub S. Applying Formula 3 to this produces Formula 7, which is delta S sub max equals ln omega sub E over omega sub S. In general, this shows the direction that applying energy to a system will move the entropy of that system. However, the actual change in entropy is a result of the amount of energy applied to the system. The amount of energy applied to a system is measured in the number of component parts of the system to which it is applied, which is less than or equal to the total number of component parts of the system. In a system with a variable omega, where energy is applied such that sigma is much less than n, and omega sub 1 is less than omega sub s, which is less than omega sub 2, an anomaly can occur when omega sub 1 is less than omega sub e and less than omega sub s, or omega sub s is less than omega sub e and less than omega sub 2. In such cases, the change in omega is limited to the range of omega already within the system. This is because the anomalous change occurs only because the energy is affecting parts of the system with an absolute value of omega sub s minus omega sub n greater than absolute value of omega sub s minus omega sub e. The entropy change formula shows the difference between construction work and a bomb. Construction work has an omega sub e smaller than the omega sub s of the raw materials, while in a bomb, omega sub e is larger than the omega sub s of the raw materials. A good illustration is to consider what happens when a system is heated and cooled. It is known that heating a system produces a delta S greater than 0, while cooling a system produces a delta S less than 0, and Formula 7 shows why this occurs. At a molecular level, heat energy is applied randomly, such that omega E equals omega S max. For any system where omega S is less than omega S max, then heating the system produces a delta S greater than 0. This result is shown by delta S equals K ln omega sub E over omega sub S equals K ln omega sub S max over omega sub S. When a system is cooled, the electromagnetic forces between the molecules are better able to guide the molecular motion such that the energy of these electromagnetic forces are applied to the system as a whole with omega sub E equal to omega sub S0, where omega sub 0 equals omega sub S at absolute 0, such that for any system when omega sub S is greater than omega sub S0, cooling the system produces a delta S less than 0. This result is shown by delta S equals K ln omega sub E over omega sub S equals K ln omega sub S0 over omega sub S. This principle can be shown to apply to all systems since the analysis is both system and path independent. The basic principle is that adding more randomness to a system makes it more random, and adding more order to a system makes it more organized. Prediction 1. The general application of energy to a system in a manner more random than that system will increase the entropy of that system. Prediction 2. The general application of energy to a system in a manner less random than that system will decrease the entropy of that system. It is already known that conservation and degeneration are observed in natural processes, while the improvement processes needed for the evolutionary model are not. The present principle goes beyond the earlier concept, not only showing why this is the case, but also providing the basic thermodynamic principles that set the process types apart. It shows that degeneration results from energy being applied to a system in a random manner, such as heat and radiation. Conservation of order and complexity can occur because it requires no net change. Also, such a conservation system already possesses the order and complexity it needs to maintain itself. Since a spontaneous improvement process would by definition require order and complexity to be produced where none exists, and the present principle indicates that this is impossible, it shows why such processes are not observed. The reason for the Law 1.5 label, while clearly not official, is to illustrate the fact that this principle belongs between the first and second laws of thermodynamics. The reason for this is that the first law is clearly more fundamental than this principle. It is actually more fundamental than either the second or third law. This is because it actually explains why they work. It explains the second law of thermodynamics because heat is extremely random. As a result, unless a system is at maximum possible entropy, it will be increased simply by its internal heat. With the third law of thermodynamics, on the other hand, the system is losing heat, allowing the lower entropy energy of intermolecular and atomic interactions to take over, bringing the system towards a minimum entropy. This principle has profound implications for the idea of a naturalistic origin of life. The simplest possible living cell has an omega sub C equal to omega sub S. Energy can be applied to a non-living system in three natural ways. Molecular motion, that is heat, where omega sub E equals omega sub H. Radiation, where omega sub E equals omega sub R. And molecular forces, where omega sub E equals omega sub M. Since both molecular motion and radiation interact with molecular systems like that of a living cell in essentially a totally random manner, then omega sub C is much less than omega sub H, which is approximately equal to omega sub R. Furthermore, while molecular forces do have a degree of order to them, it is far short of the order and complexity of the simplest possible living cell. So, the result is that omega sub C is much less than omega sub M. This means that all of the naturally occurring forces that could be involved in the origin of life would drive any non-living system that is near the degree of order and complexity of a living cell towards increased disorganization, and as such prevent any naturalistic origin of life. This is illustrated by the fact that when even the simplest cell dies, the cell's molecular structure breaks down and eventually disintegrates entirely. Since information is a system that encodes and represents an abstract description of something else, then information systems would have extremely low omega sub s. Noise, on the other hand, being defined as random changes in information systems, has a very high omega sub e, such that omega sub s is much less than omega sub e. The result is that noise always destroys and distorts information and never creates it, as is actually observed in information systems. Deoxynucleic acid, or DNA, is the information storage medium for living things. Like any information system, it has an extremely low omega sub DNA equals omega sub s. Likewise, mutations apply energy to DNA such that omega sub m equals omega sub e. This application of energy has an extremely high omega sub m, so that omega sub DNA is much less than omega sub m. This can only result in the information in the DNA being damaged or destroyed, and thus the entropy change equations reinforce the observation that genetic mutations tend to be harmful. These results mean the total collapse of all naturalistic methods of producing information in the DNA of living things by way of natural processes. The response given by an evolutionist would be to invoke natural selection as a solution. To qualify as an adequate solution, however, natural selection would need to apply energy to DNA with omega sub ns equal to omega sub e less than omega sub DNA. As it turns out, natural selection is incapable of meeting the above requirement. Note that natural selection does not have a well-defined objective, which would be needed to have an omega sub ns less than omega sub DNA, since each DNA instruction has a well-defined meaning within a cell. Furthermore, natural selection does not apply energy to the DNA under consideration. In fact, natural selection does not act directly on DNA at all. It only reacts to the traits that existing DNA produces. As a result, there is no omega sub ns to be applied to the DNA, meaning that natural selection is totally incapable of increasing genetic information. It has been shown that living systems are generally conservation systems, and that the increase of their entropy over time is slower than that of non-living systems. This applies not only to individual organisms, but to entire created kinds as well. The present principle not only applies to both living and non-living systems, but allows the earlier concept to be expanded by showing why this is the case. The reason why living systems are generally conservative is that they apply energy to maintain themselves against degeneration, such that omega sub E is approximately omega sub S. But they increase their entropy because no matter how close omega sub E is to omega sub S, it is still always a little bit greater than omega sub S. As such, living systems will increase their entropy over time, but slower than a non-living system. Mathematical generalization, this is the formula for statistical entropy when the probability of all microstates are equivalent, where omega equals the number of possible equivalent arrangements. However, some systems do not have equally probable microstates. Here is the formula that describes entropy for this general case. S equals entropy, K equals Boltzmann's constant, 1.38 times 10 to the negative 23 joules per kilogram. P sub I is the probability that the system is at a given microstate. This is the general formula relating entropy to microstates of varying probabilities. Here this general formula is applied to a change in entropy, resulting in Formula 9. This results in the generalized version of our formula for the application of energy to a system. Formula 10. It has been shown here that when energy is applied to a system, the degree of randomness of the system moves towards the degree of randomness of the applied energy. When energy is applied in a manner more random than the system it is applied to, then the system's entropy increases. When energy is applied in manner less random than that the system it is applied to, then the system's entropy decreases. This represents a general concept of how applied energy affects a system's entropy that describes any application of energy to any system. Furthermore, This provides a solid answer to the argument that a naturalistic origin of life is consistent with the laws of thermodynamics, because the Earth is an open system. The argument fails because that energy is applied in a manner far more random than the high degree of organized complexity of even the simplest living cell.